3G, which was about 5 megahertz if you look at the WCDMA world, and if you look at the CDMA world, around 1.28 megahertz or ballpark in that range. 4G brought it all the way up to 20 megahertz, and with CA, you can do up to 100 megahertz. What 5G tries to do is get a bandwidth of about 100 megahertz in frequency range 1, which is till sub 6, and a maximum bandwidth of around 400 megahertz in millimeter wave. And considering the same spectral efficiency, you end up, same spectral efficiency as LTE, you end up with speeds of about 20 GB on the downlink and 10 GB per second on uplink. Apart from that, it intends to reduce the latency to bare minimum. What I mean by bare minimum is once the UE gets a downlink channel or a downlink assignment, the ARC ACNAC, everything gets finished in 1 millisecond, while in LTE, it takes about 8 milliseconds for it to finish, and this is the best rosy day scenario. So that is another of the key advantage that 5G has. Apart from that, 5G is structured in a manner where it can serve different purposes. It can serve purpose of mobile broadband, it can help CIoT devices, it can help mission critical devices, everything almost with the same radio frame structure. When we look at LTE had a rigid 10 millisecond frame with 1 millisecond subframe, and if you had to go for a low speed technology, then you had to actually increase the slot or the subframe duration and increase the number of repetition. 5G tries to address this with its original frame structure. The repetitions can be increased, but the frame structure doesn't need to be toggled with. So from a 3GPP point of view, 3GPP started with a goal of having release 15 non-standalone. We would come to what I mean by non-standalone and standalone in 3 or 4 more slides. But non-standalone release 15 spec to be made available by June 2018. It actually was able to do in terms of RAN 1 and RAN 2, which is the physical layer and the protocol layer. But the RAN 4 specifications, which define the test requirement, testability, and the various conditions in which the testing can happen, they are still not finalized. Apart from that, the test spec is still not complete. RAN 4 is targeting to complete NSA by August 2018. It can potentially move out to November 2018, and RAN 5 would finish its protocol plus RF-RRM by November 2018. The protocol spec is already released and is available, but the RF-RRM spec is not yet available. Again, by November 2018, we would get RF, no RRM, no DMOD, both of which are currently looking at around February 2019 timeline.
What is the status of SA?
So SA initially was targeted for February of 2019. It has been pulled and declared complete in June 2018. But the RAN 4 specification is still not complete, so it would be again aligned to August and November timeline. So option 2, which is one form of SA which CMCC is looking for, that is what we would be getting by August 2018. And option 3, which is the form of NSA, most of the other carriers are looking for, we would get it by August or November 2018.
I don't know how many of you are kind of really aware of what is the RAN 4 scope, and when he said NSA and SA just completed, but here he's telling RAN 4 is not completed both NSA and SA, right? So there is a difference. What is completed and what is not completed? So are you guys aware of the 3GPP RAN structure, the ARC structure? There are like 5 working groups: RAN 1, 2, 3, 4, and 5. RAN 1 mainly works on the physical layer aspects of any technology, right? Either 3G or 4G or 5G. So their scope is only the physical layer aspects, how your mobile should communicate with the base station, right? So that is their scope. RAN 2 works mainly on the layer 2, layer 3 protocol kind of aspects. So when we say NSA and SA specs were frozen for release 15, it is from RAN 1 and RAN 2 perspective. So the physical layer aspects and the protocol layer aspects are defined as of now. Okay, but RAN 4 scope is mainly to determine what is the minimum performance, okay, that you can expect from a mobile, okay, under release 15, right? So those minimum performance expectations were actually simulated using some models. So that part of the work is still in the works for both NSA and SA. So that is what the first line says. Okay. And then once they define the minimum performance requirements, RAN 5 will take those minimum performance requirements and develop the test cases. So the scope of RAN 5 is the test specification, writing the test cases for the requirements. So the last two parts are remaining, the first two parts. So at least for your understanding, right, if you want to know what, okay, physical layer procedures or protocol procedures that 5G kind of proposes, you can go and refer to those corresponding specifications.
RAN 3.
RAN 3 mainly works on the network like base station, right? There are some base station specific requirements, how to communicate with the base station, and the other side, how to communicate with the core network. So that is their the course.
Do we participate in RAN 3 at all or no?
There are few folks, very few.
Okay.
Like earlier, with Dino used to attend RAN 3.
Okay.
Later he moved to RAN 1 and then RAN.
So TBST doesn't participate in that.
Some they may, but very limited. Our focus is mainly RAN 1, some part in RAN 2, and then RAN 4, certain, and RAN 5. From MST, we participate only in RAN.
Only in RAN 5.
Only in RAN. From MST, because that is their,
Yeah.
I mean, the test scope is with them.
Okay. So what NR promises? NR promises low latency, very large bandwidth of 100 megahertz for sub-6, 400 megahertz for millimeter wave against a single carrier of 20 megahertz in LTE. Carrier aggregation and dual connectivity, these two features were introduced in release 10 and release 12 specification of LTE, but they are there by default since the beginning of 5G NR. There is a new channel coding LDPC for data and Polar for control. And then there is front-loaded reference signals which are very much similar to Wi-Fi in a particular subframe. You come to this LDPC, Polar, etc. in the physical layer session which you do in the next week. Apart from that, it also targets low latency and extreme reliability. The lower layer and RAN 2, or essentially the protocol stack, is already scaled, taking into account various applications like machine type communication, unlicensed CV2X, broadcast, satellites, etc. Most of these features form as part of the release 16 of the specification. Release 15 just targets mobile broadband, and as an extension maybe smartphones. NR is much more configurable. We are not as complicated as 3G WCDMA release in 99, where the same configuration could have been done with radio bearer configuration, physical layer reconfiguration, transport bearer configuration, or as simple as release 8, where everything happens in RLC connection recon, a single message. It's a balancing factor in terms of protocol stack between these two. What it also tries to achieve is a single transmission mode, unlike LTE, where release 8 had 7 transmission mode, and by now we have up to TM10. But NR targets to have only one transmission mode right throughout the, or at least for release 15, until some compelling reason comes up for release 16.
I think from an IDF perspective, okay, which I'm kind of interested in. So you guys can actually pick up these topics which are upcoming, right? Release 15 anyway frozen, so we can't do much from a standardization perspective. Of course, when it comes to implementation, so we can actually kind of think through and come up with different ways of implementing the same requirement. So those are the things that we can do on release 15. But if there are some new things that you want to kind of propose, so then the future NR release, which is like release 16 currently being discussed. So the main topics are listed here. So massive machine type communication. This is one of the topics that being discussed, which will definitely be part of release 16, which will be enhancements to your already existing either eMTC or NB-IoT. And then industrial IoT is another topic where to provide a Ethernet kind of reliable kind of communication through wireless channels. So that is very important. If someone like in a factory, they want to deploy 5G, for their machine type kind of communication. So that is one. Then extending the 5G for unlicensed. Now we have LAA or multifier, right? So the same way, can we extend 5G to unlicensed band, either with assisted access or completely deploy 5G in the unlicensed band. And then you can actually set up some private networks within like office or within a factory or something like that, right? You can have 5G private networks as well. If there are like, if you come across some kind of process or procedures that are that can help to set up these things, right? You can actually propose. And of course, yeah, C2VX, the enhancements to vehicle to vehicle communication, or V2X, right? So those are some of the enhancements that they are targeting in the system.
So what is 5G doing new? Essentially, it is adding a lot of bands which were not even existent. There are 4 bands, for example, in greater than 10 gigahertz range, which 5G adds as an initial launch supported band. Apart from that, most of the LTE segment had less than 3 gigahertz or up to 3 gigahertz as a transmission network. 5G allows additional bands between 3 to 6 gigahertz. Of course, from a testability point of view, when we are doing millimeter wave, you cannot use any connectors. It's all OTA radiated measurement testing. You would have actually new procedures for millimeter wave operation like beam sweeping, beam management. The cell size of a typical millimeter wave cell would be few tens of meters. And to get a slightly more extended cell range, you might have to deploy multiple antennas. There would be about 128 antennas on the base station, 32 on the UE side, to give you that gain so that the range could be extended from few tens of meter to 100 of meter, that sort of thing. Apart from that, 5G initially started as a TDD only technology, but then because of push of certain North American carriers, FDD was added. And but the physical layer structure is still very TDD centric. It allows switching between downlink and uplink inside one single millisecond. Hello. वो मैं भर दूंगा. Hey, can I call you in 10 minutes? Sure. Okay. Apart from that, till now in LTE or any technology, you had some always-on signal. What I mean by always-on signal is a pilot channel, reference signals, RS. 5G is a technology where actually it targets to increase the spectrum utilization by removing the always-on signal. The reference signal would not be transmitted always from a base station. They would be periodically transmitted every 120 millisecond so that the UE can detect. But once that window of 5 millisecond passes off for that particular reference channel, for the next 120 millisecond, the entire block, the entire thing could be allocated for pure data. Apart from that, LTE coexistence was planned, because of which there is a weird channel raster where for bands which support LTE as well, use a channel raster of 15 kilohertz. But for bands in FR1 which don't have LTE transmission supported, use a channel raster of 100 kilohertz, and in millimeter wave you end up using a channel raster of around 200 kilohertz. So there are multiple configuration on the physical layer that a UE is supposed to support as and when it moves from one band to another band. Apart from that, there is a new concept where an actual network can be deployed in a wider bandwidth than what the UE supports. For example, UE supports only 100 megahertz bandwidth in FR1, but a network can deploy its deployment in FR1 for a 400 megahertz channel, and then have 4 UEs split between the 100 megahertz in that 400 megahertz bandwidth. By this way, the capacity that can be given by one base station to, the number of UEs that can be supported per base station increases 4 times to what it is there in LTE. And on the downside, for a UE, we have to support a 400 megahertz bandwidth in a particular band, but then you could be limited in one particular 100 megahertz bandwidth.
So it's a mandatory to support 400 megahertz band.
You support a particular band, the band could be as wide as 400 megahertz wide, and the network could actually keep you in a BWP of only 100 megahertz. So there is a BWP that you can signal that I support.
For each individual UE, this is the maximum allowed bandwidth
that I can support.
What is the saving for UE here?
There is no saving for the key saving is when your LNA is not scanning the entire 400 megahertz or the entire bandwidth of the system, then the amount of time the LNA is active reduces, which means your power that is used to remain active from a sleep mode reduces actually. So there would be a current gain in 5G versus say 4G. For example, RJL can deploy a 20 megahertz bandwidth and then ask the UE only to focus on the 5 megahertz, which is its portion to monitor. Outside of that, since it doesn't have to monitor, the LNA could be active and can do a scan of 5 megahertz in probably few milliseconds, whereas for a 20 megahertz, it might take few tenths of milliseconds. So that is one of the advantages that you get in terms of power saving. Network load balancing is self-evident. You can actually have multiple UEs split across the bandwidth and then use them in those particular areas.
That network load balancing happens today also, in terms of RB allocation, right?
Correct.
So how is it different in 5G? How will network load balancing help with this?
No, so the key thing
load balancing, it can be like, for example, like asking mobiles not to ratch. That could be one way, right? But as of now in 4G, there is no mechanism where I can actually direct the UEs. Okay, you monitor out of 20 megahertz, you monitor only the first 5 megahertz, right? So that I can allocate for the other set of mobiles, the second set of 5 megahertz, third set of 5 megahertz, and the fourth set of 5 megahertz, right? So there is no concept of like bandwidth, okay, part concept in 4G. But in 5G, you have this wide bandwidth where you can actually kind of logically split this bandwidth into multiple chunks and ask a set of mobiles only to monitor this, right? And that is how you are probably able to get, accommodate more number of UEs.
I think they're trying to simulate FDD concept in TDD networks. Something sort
This can be even done on FDD where your uplink is on a different band.
Right. So even then, right? Today, indirectly, it is that we are even though
I think from the uplink side you think. So the ratchet channels are fixed.
Yeah.
Right.
From
So
load balance,
any number of UEs, whether it is like 5 megahertz, 10 megahertz, 20 megahertz, okay, the ratchet slots are fixed.
right.
So those slots has to be kind of utilized by all the ratchet memories. Now by splitting this into chunks, I can actually have some ratchet slots in this 5 megahertz, some more ratchet slots in this, where for this 5 megahertz ratchet slots, only the mobiles assigned to that slot will be able to access, not the other ones, right? Somehow that load balancing can happen from the uplink side. Of course, there might be some other
only the initial access maybe.
That is one kind of load balancing, but there could be multiple others. But from power perspective, you assume like if you are on a VoLTE call, you are getting like hardly like 10 to 15 kilobits per second. Why to monitor that big chunk of 400 megahertz, right, entire bandwidth? Okay, all you need to do is just decode this, right? So that could save the power rather than processing.
UV side.
UV side, exactly.
Is this more prominent for millimeter wave?
No, this is in FR1 and FR2 both. So some of these, especially greater than 3 gigahertz channels, they are actually very wide. Less than 3 gigahertz, they are typical 20, 50 megahertz, less than 100 megahertz sort of thing. But greater than 3, they are all greater than 100 megahertz channel. And then in that, the FR1 UE could be actually limited to a 50 megahertz block only. Or those are some of the concepts that people have thought about. How actual deployment might happen, that can change. Apart from that, in LTE, as and when you upgrade your release, you move to a next set of version, the devices which were in the, there is a release 8 UE in a release 12 network. The handling of a release 8 net UE to release 12 is not, in a release 12 network, is not very straightforward. But what 5G tries to do is, right from release 15, it tries to say these are some of the concepts that you need to, for example, wider bandwidth would be a release 16 edition. So in FR1, you could do up to 400 megahertz in release 16. That logic, that emphasis on splitting the bandwidth into multiple bandwidth parts has been built in right from release 15, so that as you move further, there is a certain amount of forward compatibility on the UE side as well. This is something which is not yet clear how it would pan out, how it would actually get visualized in future, but probably a topic of interest in upcoming sessions.
One question. The always on signal minimization, doesn't that impact handovers?
It impacts mobility to a great extent, and this is some of the things that probably once we come to the physical layer aspects of the story, we can talk about it, or when we go into a more focused discussion from here, that would be one of the things, but this is just a sort of introduction session. There was another query?
For BWP, the handset is supposed to monitor only one part? Or
only the BWP part. So if you have been allocated
5 megahertz chunks as an example, the UE is not required to monitor.
No. You would be signaled, right, when you are from LTE and trying to go to 5G, you would be signaled this is the BWP part that you need to monitor, and you monitor only this, you don't go beyond that.
No hopping.
No, hopping inside 5 megahertz, yes, possible, not outside of 5 megahertz. Okay. What remains same? Waveform essentially, which is OFDM, it remains the same. We call it as TP OFDM, but it is essentially the same OFDM which is used in LTE. The primary cell concept versus active set still remains same. You still don't do any soft handoff. There are some beam management aspects where from the same base station you can actually track multiple beams, and then this concept is very similar to WCDMA active set and finger management, but essentially still it is restricted to one cell. From a physical layer channel structure, it actually is more or less similar to LTE, except that there is no more PH, there is no CFITch, there is no cell-specific reference channel, and there are two new channels which are added specifically for millimeter wave. One is the phase tracking reference signal and another is the tracking reference signal. The objective of phase tracking and tracking reference signal is that when UE sends transmission on the uplink, you can identify multiple UEs based on the PTRS and TRS. From a uplink point of view, PRACH, PUCCH, PUSCH and SRS. The initial equation continues to be two steps. You first detect PSS, follow it up with SSS. Random access remains the same. Message 1, message 2, message 3, message 4. Power control remains the same. The sequences that are getting used, they remain the same.
We have doubt on this. PSS is once you are assigned with some bandwidth part, right? Do network make sure that the bandwidth part had PSS?
So basically what the network is going to do is to ensure that UEs in different bandwidth part get the PSS, SSS, is to ensure that these are frequency repeated at a certain instance of time. For example, less than 3 gigahertz, PSS, SSS would be repeated every 900 kilohertz in the frequency domain. In the time domain, they get repeated once every 120 milliseconds for a 5 millisecond window. But in the frequency domain, every 900 kilohertz, you would see the PSS, SSS. As you go all the way up to millimeter wave, you would see this frequency separation getting reduced to, getting increased to about 2.4 megahertz instead of the 900 kHz. But there is a certain amount of scaling over.
Okay, but what if like some UE wake up? Our first thing is we make sure that zero frequency plus or minus 6 RB is our way of doing. Now we don't know the location of PSS. Then how we will do?
So that is one of the challenge for the UEs in 5G. This is probably some of the areas that we are going to talk as the IDS area as well.
So basically, how to determine the exact position of PSS?
Yeah, so far in LT it's fixed, right? I mean PSS, SSS location is fixed. So we tune there. We always look at the central 6 RBs. No, now he is saying that
it is not in the central 6 RB. It's actually repeated every 900 kilowatts. For example,
but that's
the
location of those.
It is not central location.
It can't really hop or transmit any.
It would be right throughout the entire bandwidth in a 900 kilohertz frequency split and every 120 millisecond for a period of 5 milliseconds.
I agree, right? You can transmit on this what you call the channel and then this channel and this channel. But with respect to the time, some reference, that has to be fixed, right?
That is fixed.
No. So for example, in LTE, when you go to this bandwidth, the PSS SSS is in the central 1.2 or 1.02 megahertz. When we come to NR, you would see a PSS SSS coming in a grid-like structure. At different instance of time. Now, for example, when you move out of LTE and move into NR, LTE assigns you a BWP path. It gives you a small area in which you have to monitor. You miss this, then you have to wait for another 120 milliseconds for this to come back at this time. Otherwise, this is like a grid-like structure actually.
So this is for a handover case, you are saying.
No, even
This is initial access. Initial acquisition.
Problem is we don't know the bandwidth.
The first specification is non-standalone, wherein you would always camp on LTE, initiate a call on LTE, get a data and IMS bearer attached on LTE, and you are configured for a measurement of a NR channel. When you
agree, you see, within that assigned bandwidth part,
There is a clear demarcation.
Position in the first, for example, the diagram that you wrote, right?
Correct.
So the first maybe 5 subcarriers, right? For that duration will carry the PSS or SSS. That is like fixed, right? Within that sub bandwidth part.
No, that also would change based on which frame subframe you are.
Agree.
No, what I'm trying to say is,
But if you
when I come back,
like fixed.
when I come back next time, maybe it won't come in this location. It can come actually in this location, here, and then further over here, here. So there is a equation, mathematical equation, which actually specifies where you are going to find your. This is known as a SS block. So PSS, SSS, and PVC all in one package, in one single box would be transmitted, but at different frequency location to avoid interference.
And also, Ashok, like when you boot up, right?
Yeah.
We don't know what is the bandwidth of the network.
Correct.
So you always assume some center frequency.
No, you would come to a LTE band.
I mean,
Always. LTE bandwidth is slow.
No, I'm talking of standalone only.
In case of standalone, yes.
So we don't know, right? So then in that case, it's how much 100 megahertz, 500 megahertz, we don't know, right?
No, but when you do kind of sweeping, right, the power sweep, you can actually identify approximately if the network is transmitting, let's take 100 megahertz, then you see the energy only in that 100 megahertz, right?
This is
Like
how actually even the
you
LTE
take
band
like
scan happens today.
That happens, but still, even though you do a scan, right? But initially, you always look at 1.2 amperes. You don't, because you don't know about the bandwidth of the signal.
So there is
It's not 100% accurate, right?
There is something
It's a
known
power
as the
only.
GSCN frequencies which are defined.
It
It's
was
a global sync channel number.
Yeah, it works very well at a good channel, but when you are a noise floor, then you don't know where is the boundaries. Then it's very difficult to find.
So probably we can take that next week.
Yeah.
Okay.
In this, one last question. So whenever this grouping comes, right, should the reference signal also be part of it? So you said PSS, SSS,
PVC. These are the three reference signals.
reference signal also comes along.
Correct.
The TRS or
So you have like PSS first, SSS at the last, in between PVC.
and you will have the TRS or the PTRS also coming.
The PTRS and TRS is only for millimeter wave. Yes, they would also come once you are in call. They are used, for example, in a sort of beam management where, for example, to identify a base station can have up to 128 beams in millimeter wave. To identify beam number 102, 1 to 127, you would send TRS. Once the UE attaches to a particular TRS, then to continue the call, to continue the radio link, a PTRS is sent to the UE to give it a reference so that the UE identifies the phase shift. And with that, the Doppler. And with that, the amount of distance that it has moved out of from the base station point of view.
You said there is no EC pitch and pitch channel.
Correct.
So how the UE would know the control channel part and the user part?
So in LTE, your control channel or the aggregation, CCE aggregation was given by piece of pitch. You don't have that control channel aggregation concept over here, so you don't need a piece of pitch per se. The only challenge is PH, where you send a ACNAC. Now that is getting bundled in your PUCCH itself instead of being on a separate physical layer channel. It happens in the same 1 millisecond. Everything happens in the same 1 millisecond.
Downlink, pitch and in downlink. So in downlink PDSCH, you are saying it could be bundled.
No, PH was essentially
comes along DCA0.
Yes.
So DCA0, you don't, even for NB-OT, you don't have a PH. Right? So you get that information in the DCA. With NDA toggling, you'll get to know whether it is a new transmission or a return.
okay. So so NR supports multiple carrier frequencies. For example, LTE only used to support 15 kilohertz RE, whereas NR supports 15, 30, 60, 120 and 240 kilohertz, where 15, 30 and 60 are for sub-6, 60, 120, 240 are for millimeter wave. But as I said, actually the key thing about spectrum utilization is in LTE, only 18 megahertz of your channel was a usable PDSCH usable channel. In case of NR, it goes in certain configuration to as high as 95 to 97%. So you get that 5 to 7% higher spectrum utilization in the same bandwidth. Okay, some of the common terms that are used is ENDC, which is E-Ultra and NR dual connectivity. G node B is the new NR node B. Subcarrier spacing, SCS. I forgot the essential term for LTE, but essentially the 15 kilohertz resource element. FR1 refers to sub-6 bands and FR2 refers to millimeter wave. Millimeter wave starts after 24.5 gigahertz. Apart from that, the various physical layer channels. You want to do?
Hey, can you talk about what is the immediate PL that we have and what is the use case and that?
I'm sorry.
Qualcomm point of view, what is the immediate PL that we are working on with respect to this, and what is the practical use case from a deployment or end user case scenario for the terminal?
Okay, so now we have two products, right? At least immediately we are kind of working on SDX50, which is our first 5G model, which will support the non-standalone mode of operation. Okay. We need to have LTE to even establish a 5G connection. So that chip is mainly for our trials that we do from now until mid of next year or so. Okay. Mainly it will be for trial purpose. So by I think this September, October, SDX55 will be available. So that is our first commercialized model, or at least modem which will be commercialized. So that will support both SA and NSA. So both standalone and non-standalone is supported on that, along with the support for all racks, okay, including your 2G, 3G, and all other 6 or 7 different technologies, right? So that the first commercialization is planned, using the SDX, or rather SDM855 or SDM8150. That will be paired with SDX55, okay, and be commercialized as a fusion product, okay, to serve the smartphone market, right? So mainly, at least the targeted countries are China and obviously North America. CMCC is interested in SA as of now. Of course, they might also adapt non-SA, okay, but North America might initially go with only non-SA. At that, then there are like 2 or 3 additional PLs planned. So one, pairing SDX55 with the next year premium chipset, which is SDM865 or SM8250. SM8250 plus SDX55 will be the next kind of product which we will commercialize. And then, I don't disclose this one to outside, but there is a value tier chipset, Saipan, which is kind of an integrated kind of apps plus the modem. Okay, the first integrated solution is coming up, the value tier for the first time, and that will be CSing towards the end of next year. Okay, that will be for worldwide deployments.
Okay, so moving on, essentially how a operator can actually move from a 4G only network to a 5G network. So essentially you have a eNode B and a EPC, which is your standard 4G LTE network. You add an additional node, a NR base station or a card in your existing LTE base station which supports NR user plane, and you are ready for option 3 non-standalone. The terms that I'm going to talk about, like option 3, option 4, option 2, etc., we would discuss in a couple of more slides, so we can hold on to that. But what it essentially means is an operator, just by adding one additional base station unit, can migrate to 5G. This he can further evolve by adding 5G core, which is a next generation core, and the next generation eNode B. With this, he can actually either do a non-standalone deployment of option 7 or a standalone deployment of option 5. Further, he can actually split the NR base station into a control and user plane separate 2 entities and create a standalone option 2 and option 4 configuration. Option 2 configuration is the one which is more favored by CMCC. Option 3 is for rest of the world. The key thing between standalone and non-standalone, the terminologies that I used, is that in standalone, a 5G UE operates connected with an anchor G node B without a need for an LTE radio connection. It can add a secondary LTE connection after it establishes a NR call, but it doesn't need LTE to be alive. Whereas in case of non-standalone, the UE is connected via an LTE radio connection. So it essentially needs to come up with a eNode B, and then it could be moved away to a secondary 5G NR connection. Now to support non-standalone, you can do multiple bearer option. One is non-split, wherein the bearer comes exclusively from one of the technologies, which is either 5G or LTE, or split, where the user data could be split between 5G and LTE. So simultaneously you can receive data from LTE and 5G, or you can receive only from 5G or only on LTE. This is known as a split architecture. So these are the different standalone configurations that are standardized in 3GPP. Not everything is popular. For example, option 1 and option 5 more or less is out of contention. Nobody is going to deploy. Option 2 and option 6 are two potential configurations which could be deployed. What option 2 intends to do is deploy a G-Node B and a 5G core for control plane function and user plane function, and a 5G only UE. It doesn't need to support LTE, WCDMA, GSM, etc. on the backend. Or in case of option 6, where you can use the old LTE core, but a new G-Node B, and which actually works with a 5G supporting only device, again, which doesn't have any back support of LTE, WCDMA or GSM. The other configuration is you use the existing infrastructure, just upgrade the eNode B to support 5G NR physical layer and deploy option 1 configuration. It was realized that with the latency of less than 1 millisecond that is required, the current eNode Bs would not be able to scale up. So option 1 is not at all a possibility. The other possibility could be that you have a next generation core, the old eNode B, and use a standalone mobile. Again, this also is not finding much favor because of the restrictions on the eNode B. Any question on this? What happens to user plane and the control plane in case of standalone? If you compare LTE versus NR, essentially there is no difference in the user plane between in a standalone LTE and standalone NR bearer. There is essentially no differences between LTE and NR. But when we move to non-standalone, we would see some slight differences. In the non-standalone, option 3 and option 7 are the two most popular configurations. In option 3, there are three different possibilities. Option 3, essentially what it talks about is that there is a next generation eNode B, an evolved eNode B, and you still use the old eUtra packet core. In case of option 3, the user plane data from the evolved EPC comes all the way to LTE eNode B. Then a portion of that user data can be redirected, portion or the entire eNode B data, user plane data can be directed towards the 5G Node B, and the UE could be connected to both LTE and the 5G base station and get user data from both of them. So this becomes essentially a sort of dual connectivity configuration. Or option 3A, where the control happens on the LTE side, but the user plane data comes directly to the eNode B, the G-Node B, and the G-Node B sends the user packet to the UE. Option 3A is not finding much mileage. Option 3 and option 3X are the two common configurations that we are seeing. In option 3X, the user plane data comes from EPC, goes to 5G eNode B. 5G eNode B splits the packets, sends some of them to the LTE eNode B, and you get data from both LTE eNode B and 5G eNode B. Or you can get data only from 5G eNode B, but there is essentially a interface between LTE eNode B and 5G eNode B.
I have one. The first option 3 won't be the bandwidth limiter. Those are fixed or S1U. And will the older node Bs have that interface?
No, basically the way the networks can work around is, I know I have to send about 500 GB to a UE. I can ensure before initiating a network call, a RAN call, I ensure the transfer happens from the PGW all the way up to E node B, and the 500 GB is split between the E node B and the G node B, 250 GB each, and then transmitted. So then there is no latency as such. Or the basically the spec allows for wider. So essentially the connection were all even T1 based, which are now getting migrated to Ethernet based. I'm not actually discussing more of those options in this because our focus is more on the radio architecture point of view. But the infra also is going to get an upgrade. So you would get a Ethernet connectivity, I think 100G Ethernet connectivity between the different nodes once you migrate to 5G.
No, the line can be made both. The node Bs already have this interface. I mean, they had put tested H1. The node Bs, do they have another already a spare which can support 100G or 500G, or only the infras or the equipment infra vendors who already have it, they can, I mean, not every carrier can move it. Let's say Nokia's one may have a support for adding S1U, Huawei may not have.
No, the current S1U, S1MME, etc. Okay.
S1U,
So basically,
do
query
they
is
have
like the backbone may not have capability to go to 100 or 100 GB line.
Okay.
So currently it may be 2 gig line. So
Correct.
are the Bs scaled up to carrying 100 gigabits of
No, so
data?
basically none of the E node Bs, if you notice, are the legacy E node B. They are all the evolved E node Bs.
Okay.
They need to have a software upgrade to go to speed to support 5G actually.
Okay, that's the difference. The first one is M, the other one's
ME, what is ME? MENB?
Master E node B.
Which one?
MENB.
So when we say NSA, so every LTE node should be evolved, and they have to
No.
work.
So this is not necessarily in the same network deployment. You would have all your E node Bs migrated to the evolved E node Bs. You could still have some E node Bs which are in the older release 10, release 11, release 12 timeline, and then there are E node Bs which can support release 15, and these would be a smaller cluster. Okay.
So why is option 3 more popular than 3A?
Okay, let me answer. Why option 3 is very popular than 3A relatively, because the upgrade cost is only the S1U connectivity between PSGW and ME node B. The idea is that typically the base station, most of the base station vendors would just have a NR card inserted in their existing E node B to support NR connectivity. So that is a cheaper option than to actually upgrade your PGW, SGW and support multiple new G node Bs. Right? Each PGW, SGW supports close to, I think, 5,000 or 10,000 of base stations on an average.
Mayur, option 3A, option 3X also, E node B will be upgraded, or it will be a legacy E node?
All E node Bs which support NSA, they need to have an upgrade on their, essentially because of their latency requirement.
But this will be only software.
Software plus firmware.
Firmware, but no hardware upgrade.
Hopefully.
Because if they are doing hardware upgrade, then it will be SGM.
So, what factor switching between the two, right? Between the two new
No,
radio and
this would be like a CA call, right? So you are always connected to both LTE and the 5G. Yes.
you have to
So it's like interband.
dual connectivity.
So option 3, 3A and
3X, right?
are all
what is
LTE
the
driven.
advantage?
Everything,
you are having a
all your
bypass, right?
initial registration, everything.
So what
happening
extra
on,
benefits it gives you?
and then that will be a master.
Between option 3A and option 3X.
That is your master.
The reason why you would go for option 3X is that you have your PGW or
Once you are
SGW
connected on
has been upgraded,
then
and now you can split your bearer in 3A. Whereas in 3A, your bearer cannot be split.
So better always going via that. Okay. Once you are connected to that, then you are getting like two.
So basically, in 3X, the UE acts as if it is getting two data links. Whereas in 3A, it gets only one data link from the NR.
Okay, so you are getting NR side, PDCP.
There is no user plane data coming from the E node B.
3X, which
So
is
that is the main disadvantage of 3A, and why 3A is
RRC level,
out of contention, more or less.
at the signaling level. Okay, so they each of them have their own benefits, but
We can
3A
have
is
one talk. I think. Let's keep it to that.
One last question.
Yep.
Does the UN really need to know about common?
No. we only need to know, basically this is supposed to be an IDF generating session to understand, how your device could be actually moving between an option 3 or an option 3X network, which would be the most common configuration, and then what you can do about it.
But it's not signal to the hand.
The device never comes to know. Correct. So any of the option, I mean, you only when it's so between option 3 and option 7 also, you won't come to know what is happening to your core network. For the UE, you are getting a data packet, you are getting established, a control channel is getting established on the LTE side. You would get a LTE packet on the G node B. If you start also getting LTE packet on the E node B, you can assume you are in option 3X or option 7X, because you are getting two simultaneous user plane packets from both LTE as well as G node B. But if you are not getting that, there is no way to identify that you are in option 3 network or in
But
option
that has
3.
to be indicated to the user, right? How it is getting, whether it is getting the data on both FE and
So
5G
that
or on only one.
That happens with a RRC recon, but a option 3X network can actually configure you in an option 3 manner where you get only NR.
It can.
So 7 is mirror of option 3, but with a next generation core. So instead of using EPC, you deploy a whole new network of 5G, add 4G base station, and do. So that is one of the reasons why option 7 is not finding much takers.
because for option 7 you have to upgrade the core as well as RAM.
You have to deploy a new core and buy a new 4G base station. So now NSA relies on dual connectivity for establishing a call. It can do a split bearer or a single bearer. When I mean by split bearer is that both LTE as well as NR, the data is split at the PDCP level and then sent to the UE as two different packets, or it can only send it via the NR network only.
So Mayur, SCG and MCG, both bearer can be split or only one bearer can be split?
You can do split bearer via either MCG or SCG. If you take release 12 LTE, it used to support split bearer only via MCG. The secondary cell cannot do a split bearer. That is, the packet can't come to the second cell and then be routed towards the first cell. But in case of 3X, that is what happens. The packet comes to the G node B, split, and something is sent to the LTE node B.
Okay.
Okay.
So uplink also has to go in a split way.
Uplink could be NR uplink only, or LTE plus NR coexistence uplink.
So then UE has to tell this bearer or this bearer.
The data path is always on the NR as of now, but control would be both on LTE as well as NR.
No split.
So PUCCH would be transmitted on both NR as well as LTE.
Mayur, one basic question.
Uplink data can be sent even on LTE, right? Like downlink. Okay, I'm downloading the data. I'm transmitting only some bare minimum uplink data, right? That can happen only on LTE, right?
That can happen. I mean, if you don't have much data, it depends on how the network configures you, in how it moves you out of LTE into NR.
So your question is
Like
split.
uplink C is a use case.
Theoretically possible, but we need to
Yeah.
see. If downlink is possible, why can't uplink, right?
No, now it supports. I mean, can we have NR? I mean, what are the anchor carrier? Can have uplink, or only anchor carrier is only down?
No, anchor carrier can have both uplink and downlink.
Can you go back to I think it shows both things. So on the 3A,
No, this is the
Direction. Direction independent.
yeah, it shows both, right? You're sending the PDCP on both, right? Both on the FT and you should get the act on both.
So at least from a requirement point of view, there are already requirements which states that you are transmitting on LTE, you are transmitting on NR, and this is the max power you are using on NR, and this is the max power you are using on LTE. So there are requirements already in place, which means release 15 of the spec allows for a uplink CA sort of thing between LTE and NR as well. What is the use case? I don't see a use case, but you know.
Use case might be like if you transmit, for example, for voice call, right? You can still use, let's take LTE, right, which is probably widely deployed. And in addition, if you have some data, that can be kind of sent through the NR. Just typical use.
So I'm going one level lower only at this time into the physical layer, not beyond that one layer, just to talk about bandwidth, channel rasters, and the different configurations between FR1 and FR2. So as I was saying, the maximum channel bandwidth that is supported in less than 6 gigahertz is 100 megahertz, greater than 24 gigahertz, it is 400 megahertz. The minimum is 5 megahertz in less than 6 gigahertz, and once you go to 6 gigahertz to all the way up to millimeter wave, it's 50 megahertz. So for subcarrier spacing, initially I told you could have multiple carriers in 15, 30, 60, 120, 240 to make the system little more reliable and little less complicated. In the LTE refarming bands, you would typically have 15 and 30 kilohertz. Between 1 gig and 6 gig, you would have 15, 30, and 60. And for millimeter wave, it is 60 gig and 120 gig. 240 is used only for SS block, and it is not used for any other data channel.
Are these fixed or they are recommended values?
This is release 15 fixed,
But
and nothing stops that on release 16. This can change. But would a network like to introduce that complexity? I would show one slide where I indicate how this would become scary and complex for the UE as well. So we'll come to that.
So is there a reason why minimum channel bandwidth is 5 megahertz?
I think the only reason that it was identified was that this is the most least amount of bandwidth that is deployed in LTE, and this is going to be an LTE refarming band.
Like in India, most of the operators, they have only 5 megahertz of bandwidth, right?
No, but in LTE we have this 1.2 megahertz because we need 6 PRBs for decoding the signaling.
I know going lower than 5 might not give any additional benefit compared to 4G, right? At least when you deploy 5G, there has to be some benefit, right?
So in terms of throughput, you would not see any throughput difference even, say, if you have a 5 downlink CA LTE mobile and a NR 100 megahertz, you would not see any throughput difference, probably in few 1 or 2 Mbps sort of things, would be the difference that happens at that. The real kicker or sucker punch from 5G comes because it can aggregate bandwidths of as high as 400 megahertz. Now,
so it can aggregate until 400 megahertz is what you're saying.
For
Aggregate or
wave.
okay, aggregate or is it like
No,
because
one channel.
in LTE also we can have like 31 CA, right, with 20 megahertz.
Correct. But one channel, the minimum one channel in NR is 100 megahertz. Then you can do a CA between FR1 and FR2. So then you can do 100 plus 400, which is 500 megahertz, or something lower than that.
I mean, you can have one channel of 500, 400 megahertz. With,
market for release
you can have multiple.
for LTE.
As far as I know, nowhere on the earth.
So first time it is coming with 5G.
The concept is getting,
What is that?
dual connectivity.
Actually, it was introduced in release 12.
Correct.
Now we are in release 15 in 5G. Till now, it was not in attention in market.
So in NR, for any band, you use a prefix of N, essentially. So if you look at N77, for example, it has around 900 megahertz available, but it is an FR1, so UE would be focusing only in the 100 megahertz of that 900 megahertz channel. The remaining 800, it won't scan once it is moved from LTE to NR. But say it comes in a standalone system, it might scan the entire 900 megahertz bandwidth, then get focused into a 100 megahertz and keep itself to the 100 megahertz. For FR2, there are only currently 4 bands identified: 257, 258, 259, 260. The first 2 are from US, third is from Korea, and fourth is again from US.
All are TDD bands.
All
you
are
mentioned
TDD
FDD is also in the description.
Actually, there is a more detailed, so N71 is one band which is going to be used by T-Mobile and is a FDD band, but with only 40 megahertz bandwidth.
Mayur, what is that SUL?
Okay, so SUL is a new concept that is introduced in NR. So for example, we had band 29 in LTE, which was a supplemental downlink only band. Now this is supplemental uplink only band. So you would not have any downlink capability in this particular band. You might be in a LTE cell and then this NR band is added, then you can do only uplink over here and no downlink. Use case?
Yeah.
No idea.
Opposite use case. I mean, we are asking downlink in LTE, but uplink in NR.
Emergency zone?
Oh, it's only capacity addition, right? So emergency.
Yeah, it depends on your configuration, right? So the available band, one band can be only used for downlink, and this can be used for uplink.
So you have a use case in LTE for downlink. You don't have a use case. You have an opposite use case in NR for uplink. Why would you need the uplink supplementary?
So there is this one of the proof of concept that people thought. There is a wireless charger. I keep my phone on top of that wireless charger, and that wireless charger upgrades my software to the latest version.
Okay.
Or that would be a downlink scenario. Or, for example, you are doing a backup of your entire phone on the same wireless charger, which eventually goes into the network. So,
Maybe some
It
cloud
will go to the cloud also,
where
right?
you have to kind of upload some data to the
this
cloud.
was one of the use cases that was talked about by Samsung a lot in RAN discussion.
Okay.
So you have a wireless charger which would be an NR base station.
Okay.
You kept your phone for charging, and while you are charging, the phone is able to back up entirely whatever GB of data it has to the charger, and by the time you are done charging, your entire data is backed up.
Mostly like backup or
And
uploading.
even nowadays you have a lot of data sharing, right? WhatsApp videos and all that. So those are all uplink. So it is useful.
But most of them would be few hundred MB.
Yeah. Yeah,
Whereas
200
we are
MB.
talking
yeah,
about.
it
Anyway,
So going forward, you will have these ultra HD movies, so you need to upload a lot of data.
So Mayur, one query. So we are going up to 6 gigahertz, right? So we also have overlapping in the Wi-Fi bands. Wi-Fi bands typically require some, I mean, you have to coexist. So how is that handled? Do we do some LBT kind of stuff here also?
there is no LBT defined in release 15 of NSA. But in release 16, maybe you would see a LBT sort of model. But it is more like a brute force technique that you are going to occupy the Wi-Fi band. It's like LTE.
So we have overlap with the
The 5.1 gigahertz, there is a band actually which is defined for 5.1 gigahertz.
So how, I mean, that should have already modeled into the whole spec, right? That if it is overlapping, we have to have measures already in place.
Release 16. Okay. From a waveform point of view, this uses CPU FDMA, but just because there is no always-on signaling, you get spectral utilization of greater than 90%. The modulation schemes are similar to LTE, QPSK 16-com, 64-com, 256-com, but there is a new modulation known as 5x2 BPSK, which is actually defined in the spec, and this is specifically only for greater than 6 gigahertz. That is for millimeter wave. The key advantage of 5x2 BPSK is since the range, the distance over which you can send the information on 5x2 BPSK in uplink would be higher. That's so control channel would get modulated for 5x2 BPSK, but this is again not very agreed and very called upon concept. But for some reason, Government of India is asking for 5x2 BPSK support in NR. You have LDPC codes for data channel and polar codes for control channel. There is no explicit DC subcarrier. So we used to have that central 15 kilohertz carrier in LTE, which is blank. It's a null. So there is nothing of that sort in 5G NR. So that is another challenge for a UE because it cannot come to know of the center of the frequency. Frame structure, a radio frame is fixed to 10 milliseconds, subframe is fixed to 1 millisecond. Now 1 millisecond subframe can have 14 OFDMS symbols. These 14 OFDMS symbols could be organized into 2, 4 or 7 slots. I'm just focusing on 1 millisecond. 10 milliseconds is too long for an hour. So now I can break this. If I use 7 symbols, then I'm breaking into 2 slots. If I use 4, I'm breaking this into 3 slots, and then there are some guard bands for 14. So 12 and 2 symbols are for guard band purpose. If I use 2, I can break a 1 millisecond 1 millisecond subframe into 7 minute slots. You can do an entire transmission in a mini slot. Downlink, uplink, ACK, everything. So, for example, you want to go for a IoT sort of environment, then I can go with seven slots, give each slot to one UE, and that way I have now only 2 symbols coming to the UE in 1 millisecond, so only 20 symbols in one full frame, which means I can reduce my speed for a UE. So it can work for the same radio frame architecture can work for a IoT environment, it can work for a cellular environment, or it can work somewhere in between environment as well.
Then you should also change your subcarrier spacing. The same subcarrier?
No. The subcarrier spacing, this is all, I have assumed it to be 15 kilohertz. Now when I increase my subcarrier spacing from 15 kilohertz to 30 kilohertz, what happens is my number of slots that are available doubles. So instead of, let's assume I am using a 7 of 15 kilohertz, I would get 14 slots.
Slots are variable.
So basically in 30 kilohertz I can have more data coming in, more symbols can come in, so my number of slots increases. For example, if I go all the way up to 240 kilohertz, then my number of slots, number of symbols, they increase as 2 to the power of n, where n is equal to 0 is 15 kilohertz. And this n, or this is also called as L commonly, this is going to be a recurring concept in NR.
It would be sent to you every UE that between the number of slots allocated to you.
It would configure the SCS for you. Based on SCS, it will determine that this would be your slot.
You have this similar to LTE, normal CP and extended CP. So you have that.
There is normal CP and extended CP, but extended CP is defined only for 60 kilohertz. It is not defined for any other configuration. So EMBMS can be deployed only if you have 60 kilohertz. Again, if you recollect, 60 kilohertz is supported only from 1 to 6 gigahertz. So it would be EMBMS can be deployed only if you have a frequency in 1 to 6 gigahertz.
See, on this slot you are going to have a new band information. Every slot. And usually every 1 millisecond you will get to know what is the grant for you.
Correct.
Now you are saying it is
In one slot, you would have a grant and you would have acknowledged the grant as well.
Yeah, that means it is
You would have
minute fraction of millisecond.
Correct. So around in 600 microsecond, probably you should be able to know, you can receive and you would have sent a ACNAC.
Granularity, you get a information and you will be doing a lot.
Yes. In 600 microsecond, you will be done with receiving the data packet and hacking it back also, and you are ready for sleep. If the data packet is
So
small.
in same slot, you have to do ACNAC also.
Yes.
You can do.
No, you can't. I mean, you will be doing ACNAC maybe in the next slot or.
No.
You
Everything
received
happens
it.
in the same
You
slot.
received it, right? You received in the same slot. I mean, how
That is-
can you transmit in the same slot?
That is the expectation of an NRU.
What
That
is
is how the latency.
That is
That 4 milliseconds is reduced by 1 millisecond. Within the 1 millisecond,
Uplink is
both
approximately,
TDD
I
and
mean, it is same as an LTE, at the same time,
You
uplink
decode
is
it
ahead
and
in
you
downlink.
respond it. How can you do
you
that?
don't. You're saying mini slots.
Ahead
Mini
of
slot now 1 millisecond has 7
So
millisecond.
you get some additional timing.
Agree, if it is
That's
a
where I didn't say
multiple
500
slot, it is
microseconds,
okay.
because that is
Within the
exactly
same
half of
1 millisecond is the lowest
But in
now.
approximately
Within that
600
1 millisecond,
microsecond,
first 2
you will be
millislots
done with your,
received, and maybe last
you would get a
2 millisecond
PDCCH grant,
That is okay.
you decoded your
what is-
PDCH, and you have sent a ACNAC as well for that PDCH.
1 millisecond. No.
But you don't have this
You
UL
have
thing.
continuous downlink slot, then first uplink slot, like that.
Yeah. TDD configurations basically.
Mhm.
You don't have ULDL config.
You do not get a uplink slot till to
So
transfer.
if it's a FDD system where you have a continuous uplink which is available already, you don't need to wait for a uplink slot.
Yes, for FDD that is fine, but for TDD,
For
based on your
TDDB, the configurations are defined in a manner of symbols. So each symbol you can change from downlink to uplink. In the time of 14 FDMS symbols, you would have done two transitions, minimum two transitions. One, you would have in the previous millisecond, you would have been in uplink, so there is a guard band, so you came to downlink. Then there is a guard band, and you did a uplink, and then guard band, you are ready to come to downlink for the next millisecond. Now, how the SCS could be deployed in networks would be, say somebody is deploying a outdoor coverage, you would use the 15 kilohertz. He is using a small cell sort of coverage inside a city, dense urban sort of network, then he can use a 30 kilohertz. So in the same network, a UE can actually simultaneously go through 50, 30, 60, 120 kilohertz sort of deployment configuration. This is what the slide is intending to show.
So my UL to DL switch or vice versa, it will be symbol time or less than.
It is one
time?
symbol.
One symbol.
1/14th of a millisecond.
So once deployed, that will not change.
The SCS, on an average, the UE, I mean the network would not change, but it got an instinct, it can send a RRC recon, move it to a different SCS configuration.
There's some null
But
period
there
before
is,
which
yeah, there would be some guard period. Basically, the RRC recon would tell in terms of frame, X frames from here, I'm going to shift to a different SCS. Now again, there were restrictions, right? Less than 1 gigahertz, only 15 and 30, then 30, 60, and then 60, 120, 240. So there are restrictions. So it is not that you would see all 6 or 7 in one.
it can change.
Correct. So we were earlier talking about bandwidth path. So this is a better slide to elaborate on that. So for example, we were talking of N77, which is almost a 900 megahertz channel. Now that 900 megahertz channel could be divided by the E node Bs between two 400 megahertz. A UE could be assigned if it is in a CA configuration 200 megahertz bandwidth path, BWP1 and BWP2, or it could be assigned 3 CA inside a 200 megahertz, or basically the UE is supposed to support one bandwidth part of 100 megahertz, but this is one of the way that the network would be splitting multiple UEs across its entire deployed bandwidth. So the network would still have a wider bandwidth, wider deployment of 800 megahertz, fit a UE in a narrow 100 megahertz to a 200, 400 megahertz channel.
So minimum is 100 megahertz, or it can go.
For FR1, it is 100 megahertz, but you can be even narrowed down to 10, 20, whatever the network wishes to.
And when allocated, it's for the entire band. Again, it's not like within that only a few RPs are.
No.
When the handset is selected, it's for the full 5 megahertz.
For the 5 megahertz bandwidth part.
UV can support multiple bandwidth paths, but SS can configure you, network can configure you to be on one of those bands. But when the allocation is given to the handset, it's for the entire spectrum. At one time, only one bandwidth path can be active.
So that's another key thing. In release 15, a UE would be limited to one bandwidth path. But beyond release 15, the UE can be, it can do a carrier aggregation or dual connectivity of NR into multiple bandwidth paths.
Hey Mayur, what is the lifespan of this bandwidth pass? Is it power on, power off, or is it?
No, in a non-standalone, once you are configured for the NR call using a RRC reconf, till the time you are assigned a next RRC reconf. So this could be as well as infinity from the network side.
Okay.
And it can be become active from the next slot only.
Correct.
So once you get this information in the RRC connection reconfiguration, it can become active from the next slot itself.
Now, the way the channel raster is defined is for bands which uses LTE, which have LTE current deployment, they would continue to use the 100 kilohertz channel raster. That is, frequencies would be defined every 100 kilohertz. But if they are not using the LTE band, or basically there is no LTE deployment, and it's a sub-6, then the channel raster is defined in terms of 15 kilohertz. So UE probably in the same 10 mega, say 1 megahertz, if it was scanning around 10 channels in a LTE reformed band, it needs to scan around 60 channels in a non-LTE reformed band, less than FR1. When you go to millimeter wave, that channel raster is around 60 kilohertz.
So the ARFC numbering remains?
ARFC number changes based on this. They have come up with a complex algorithm to write that. Okay, so this is the last slide, and this is where I actually wanted to leave to show if a network actually deploys multiple SCS. The challenge that is going to come is that in a 30 kilohertz channel, the 15 kilohertz already 2 REs have come into play. The null and the zeros would not align very well, and it would create interference for the UE. Say that even become worse between 15 and 60. You are not, for example, the peak of the second channel is still probably in a high zone of the 60 kilohertz. So this is one of the key challenges that you are going to face as a UE in NR. The only good thing, or the only thing that NR mandates, is that RB0 of the G node B for 15 kilohertz, 30 kilohertz, and 60 kilohertz, they start at the same frequency or same instance of time. Beyond that, if in 15 kilohertz you get 100 RBs, your 100 RBs would potentially get finished somewhere in this in this red segment, while for the 60 kilohertz, the 100 RBs would come somewhere later in the time. So this is one of the key challenge of NR. And when a UE comes up, for example, Qualcomm UEs are going to come up always assuming 30 kilohertz default, and then move to 15 or move to 60. Again, I am assuming it's a standalone sort of UE. Move to 15 or 60. But if it is non-standalone, then there is not much. Essentially, the UE is configured with one of the SCS configuration, and it needs to stick to that SCS configuration. Okay, so some thoughts on what we could do from an IDF consideration point of view. Now, as I was saying earlier, it is not necessary that all base stations in a given network are upgraded to a 5G NR capable base station. What happens, or what a UE can do when it moves from a NR capable base station to a NR non-capable base station? Remember, in the UE capability inquiry, the eNode V indicates that it supports E Ultra NR. When it supports E Ultra NR, the UE can come to know it supports NR. When it doesn't indicate that, it is assumed that it is a legacy E Ultra. So when a UE moves, and UE capability inquiry comes only when you are doing the initial attach. It doesn't come again. So when you move from a NR capable base station zone to a NR non-capable base station zone, or actually even more relevant is when you are moving away from a NR non-capable base station to a NR capable base station, how do you come to know that you are moving into a NR zone and you trigger a certain behavior on the UE side to indicate? So unless the base station indicates that I have a Ultra NR support, UE cannot tell to the base station that I support NR. So how can that happen is one of the idea. The other idea is, for example, you are coming up, powering on, and you want to camp onto a NR capable, but you get two Ultra signal, one from a NR capable, one from NR non-capable. Ignoring the S criteria, how you ensure you camp onto a NR capable base station? So reach out to me if you want any thoughts, if you have any, you need any directions, etc. But just remember, UE by itself cannot tell to the E node B that I support NR. It can tell to the E node B that it supports NR only in the UE capability inquiry. If in the UE capability inquiry, base station tells that I support E Ultra NR. And these three sessions I would extend to everybody, but beyond that and where we go further in depth, I would like it to be focused with people who are actually contributing more on these aspects. So filter out some of the names as we move out of the three sessions. So next 3 weeks for sure it would be extended to everybody. Beyond that, it would be on a focus group. Okay. Any doubts, questions, queries? So I left intentionally at this so that next week, once we come back to physical layer, we actually go into a little more detail of how all these things pan out.